Hello and welcome. My name is Ahmed Kibir. I'll be presenting this webinar today. So it's part of the EMOX webinar series. It's a weekly webinars. So today we're going to talk about simulation of a combined radial-axial flux permanent magnet motor. Okay. Our agenda is as follows. First of all, we're going to talk about axial versus radial flux motor or machine. Then we're going to talk about the axial radial or radial axial. Okay, it's the same thing, and we will call it just for abbreviation RADAX flux motor. Okay, show some simulation results of this RADAX motor. Including no load analysis, and we're going to go straight to a live demo. All right, so let's take a look at axial versus radial flux machine. So the radial flux machine, as you can see, these are the permanent magnet, and this one is the stator. This is the rotor, and you can see the flux path is radially, because the way the permanent magnets and of course the winding are configured. Whereas the axial flux machine, the magnetic path is actually along the axis of the machine. This is another figure here where you have the windings, the rotor, in this case where the rotor in the middle, the stator core. This is actually the axial flux machine. Okay. Now, when it comes to the radial flux machine, the flux is radially, okay, and the permanent magnets and the winding are configured differently. Here we can show you some plots using our EMOX2D and EMOX EMS software. Okay, of the magnetic flux density path. So what is the difference between these two machines? The radial machines are very old, more than 100 years old, mature, not expensive, widely used, widely available. However, the radial flux machines, they need most of the time mechanical gears, higher maintenance, and they tend to be heavier and bigger in structure. So they're more bulky. They could be okay for certain application, but in some other application where space is not available, like in aerospace and space application, where weight is very important and the size is very important. So people in the last decade or so started thinking about an alternative, what is called flux axial machine. As we can see here, they tend to be compact, lighter, applicable to direct drives. They relatively have produce higher torque and better heat dissipation. They also have some drawbacks, namely the large axial forces. So if you have the stator and the rotor, the axial machine, depending whether it's inner stator or outer stator, they tend to have a large undesired axial force, okay, which can cause the rotor to tilt and the deformation of the rotor. Okay, and that is undesirable or a drawback of the axial flux machines. Now, in addition to the axial radial, in the last few years, people said, okay, why not combine? Why not combine both radial and axial flux machine and come up with what we call RADAX, RADAX or RADAX flux machines? as you can see, this is the stator core, the winding, and this one is the radial rotor, and the radial permanent magnets. Okay, and in addition to that, we have another set of axial permanent magnet, or that they belong to the axial flux machine, and both rotor or back irons. So when you put them together, this is what you end up with. So the RADAX machine, okay, has a higher torque compared to both configuration, namely the radial and the axial configurations, axial configuration, and they also have a higher back EMF, suitable mostly for direct drive systems. Unfortunately, with this design, we still can't get rid of the large axial flux force and the higher torque ripples because of the higher cogging torque. Okay, so these are basically three machines. Let's study three of them and see. All right, so to do this, we did the simulation of RADAX machine, as you can see, with the 6 tube poles, 12 slots, 50 hertz frequency, speed 375 RPMs, not very high speed, a permanent magnet neodymium iron boron, the air gap of 1 millimeter, and the turn per slot 375. Okay, so the first set of results we want to show you obtained straight from our software EMS integrated, of course, as we can see later in SolidWorks. Again, the magnetic flux density, different plots. This is different shaded plot. This one is the entire machine. This is showing you only a section of the machine. This one is showing you only the axial flux part. So as we said earlier, the RADAX or radial axial flux machine are basically a combination of two machines where you put together a radial and axial flux machine and you end up with this new machine. This one, the magnetic flux density, and this is vector plot, and this is the animation of the motion. Okay, of course using SolidWorks motion, as we're going to see later. All right, let's look at some results of this new machine. First of all, we did the no load results to get the back EMF of the RADAX machine, and these are three phases. As you can see, the nicely sinusoidal back EMF. And let's look at this one, as probably this is the most important figure I'm going to show you today. Okay. So the blue is a classical radial flux motor or machine. Okay. This is the back EMF. The red is the axial flux machine, and the green is the radial axial flux machine, or the RADAX. As you can see here, the back EMF obtained by this new suggested radial axial machine is a lot higher than both of them. Okay, and this you can almost see it's almost the sum of both back EMF is close to the RADAX machine or radial axial machine, and this is really interesting. You know, it's really a big deal if we can combine these two machines, end up with such a back EMF. It's very interesting, to say the least. Okay, we did some other study where we studied the back EMF for this RADAX machine for a different rotor speed. Okay, 375, 600 RPM, 900, 1200, and as you can expect, the back EMF, you have a higher back EMF at a higher speed. Okay, let's compare something else. Now we compare the back EMF, and we clearly the RADAX, this new machine, new configuration, is really superior. But that's the whole story. But that's only part of the story. But if you look here, this plot, what you see that the green is a radial machine, and it's around 4 or 5 Newton for the axial force. In this case, it's Z force. Z axis is the axis. Okay. The blue, the red, is the axial only, and which is, we expect it's higher axial force. And the combined radial-axial machine actually is even higher when it comes to axial force, and this is a problem. This is we can't think about a viable use of such suggested machine without overcoming this axial force, which is definitely large compared to the axial and the radial machine. Furthermore, if we look at the torque, the cogging torque, okay, the cogging torque, we tend to have higher cogging torque for the combined radial axial machine compared to the axial and radial. Okay, so if we go previous and previous, we can see as an advantage we're using the RADAX machine, but it comes at a price, and it's really depending on the application. You're gonna need more energy to overcome the cogging torque, and one has to eventually deal with the axial force, which can definitely cause deformation of the rotors or the back iron rotors, okay, and higher again cogging torque. This one is a load analysis showing you again straight from our EMS software the magnetic flux density. This one showing you the entire machine. This one only showing you the actually the axial part of the machine. Okay, this is the torque or the dynamic torque, load torque. The load torque at 10 amps of this RADAX machine, and we achieves around 20 Newton meter. For this 10 amps is not a lot of loading anyway. Load versus excitation, as you can see, you have a higher torque as you expect at the higher excitation current. Let's look at this again. Now the load torque. The load torque of the radial-axial or RADAX machine is higher, and is almost, this one is 6 something and this one is 4. It's almost the sum of both torques. Okay, again, it's because you are putting two machines together and making one new motor out of both the axial and radial. We are having really an impressive torque compared to either one alone at 5 amps excitation. Okay, and so this is also interesting finding that we found in this during our simulation. Okay, there's some other plots just showing the load analysis, the winding loss, and the core loss for the RADAX machine. Okay, of course we can't do a motor analysis without doing thermal analysis, because that's very important. We can, because of course if you can produce a lot of torque, a lot of power, but if you overheat the machine, then you're going to melt it, so there is no point. So temperature is important, thermal loading, thermal management is important. This is the temperature distribution using EMS. I'm going to show you later on the software, and this is the thermal, the temperature distribution in the stator core. Okay. All right, so the takeaway is the following. The RADAX, or the radial-axial machine, is promising in terms of the back EMF and the torque. However, it has a drawback. The drawback that must be overcome is the axial force. You have a significant axial force that can actually deform the axial rotors, as well as the initial cogging torque is higher than either configuration, which is so a drawback. Okay, now let's just now go straight to the EMS software. Okay, and showing you the EMS is right inside SolidWorks, so you don't need to worry about the geometry because it's very easy. Okay, now let's go straight to our new machine that we are studying. So let's first of all isolate the radial rotor. Okay, takes a second. All right, so this is the radial rotor with the radial permanent magnets. Okay, then we'll show you the stator. Okay, we're going to show the stator. One second, it's coming. There are a lot of parts, so it takes a minute to load. Okay. Where's my stator core? Okay. Sometimes you have to. Okay, here you go. So you have the radial rotor with the permanent magnet, the stator, and the winding. Okay. And then we'll show you the axial rotor. And there you go. So with the axial rotor, with the permanent magnets, okay, we can now maybe exit isolate, and actually I can show you the I can show you the axial rotor. Okay, I can open this in a separate window, okay, and show you the actual. This is the configuration. So these are the back iron rotors, and these are the permanent magnets, the axial permanent magnets. Okay, so combine these two machines, we end up with this nice new machine, which we call RADAX machine. Okay, EMS is just an add-on to SolidWorks, so just in the add-in here to just click and just EMS. So it's really very handy, very powerful, because you don't need to really import, export, heal geometry, fixed geometry, none of that, okay, because you're right inside SolidWorks. Okay, so let's see, and in addition to the coupling to the CAD, we also couple to the motion. Okay, so this is your SolidWorks motion, and if you can play, you see this is the machine rotating, the RADAX machine rotating. Okay, and to couple to SolidWorks is really very easy. So in this study, okay, we're going to show you the properties of the study, this first study. Okay, when you do coupling, you say motion coupling. That's all it takes to couple to SolidWorks Motion. And you know SolidWorks Motion is based on Adams, the very popular motion software, okay, dynamic software. You choose a study. You happen to have only one study, is motion study 4, okay? You choose the moving component and the air, what we call band, the air between the moving and the stationary parts. Okay. The rest, applying material, permanent magnet material and all of that is really straightforward. We have plenty of videos showing you in our YouTube channel, showing you in details how you can apply material, apply coils, so on and so forth. Let's just move straight to results. Okay. So this one is a combined, okay, axial radial or radial axial. Okay, so first set of results is the results table. Okay, the results table, they have both the electrical or mechanical is the force and torque, back EMF, resistance, currents and energy. Okay, so one thing you can see, we can plot, say, our back EMF, okay, for the three phases, and plot. Okay, so this is the first set of results you can get. Is you can plot the back EMF as a function of time, or if you wish, you could also plot it as a function of angle, okay, which is equivalent, right? So you have the angle and the back EMF. So it's a nice sinusoidal back EMF for the three phases. Okay, these are the motion results obtained straight from SolidWorks Motion, because we don't do the motion. We rely on SolidWorks to do the dynamic or the motion. Okay, and we get the results straight and give it back straight to you. So this one just the as a function of time, the displacement or angular rotation. Okay, any of these results, we can plot them as a function of time or the axis or the angle. Okay, another set of results you can see is the magnetic flux density. Okay, so this is the entire machine. If I can animate this versus time, it's going to take a second. There are 41 time steps. Okay, and there you go. So it is rotating, and as you can see, of course, this is on the entire machine. If I want to say, I wanted to just to see my flux density, say just in the for instance, I can choose just the in the stator core. Okay, there you go. It's just the stator core. Say okay, and again I can animate versus time. Okay, of course nothing is going to change here because the stator doesn't move, right? So okay, so stator doesn't move, but it's showing the movement of the magnetic flux density coming from the rotor. Okay, I can do a vector plot. I can do this one. I can do a section plot. I do section clipping. Yes, I can do a section clipping. So I can plot on section only, and I can superimpose it with other section, and this other plane. Okay, yeah, so this is another section. Okay, I can do a vector plot, zoom to fit. I can of course animate the vector plot as well. I can, if I want to do just something, a neat feature, with just a section plot, okay, in one section only, where I want to plot one section, and I can animate, but this time versus section cut. So it's gonna take different sections and move them for you, okay, at this time step. It's cool, right? Okay. Any of these plots, the fringe vector, streamline, 2D plot. Okay, for instance, if I want to 2D, if I want to do it for the H, for the magnetic field, I want to do 2D plot. Okay, I do linear. Okay, and if I take a few points, okay, and then I can plot, okay, my magnetic field between these segments, and okay, any of these plots are available for the magnetic flux density, the magnetic field, the applied current density, the force density, the flux, so on and so forth. Okay, so there is no point of repeating them. Then I have another study where I do only axial and only radial. And you may ask, do you create another geometry for the axial only and radial only? And the answer, no. It's the same geometry, but by making some parts to air. If I wanted only axial, so the rotor, the radial rotor, I make it air, and the permanent magnet or the radial rotor, I make them air. So I end up with only an axial, and vice versa I do for the radial. So that's also very powerful. I don't need to create another geometry. Just same geometry, but by playing on the material, I can actually create an only axial, an only radial, or combined. And now let's compare some of the results I showed you earlier in the presentation. Okay, let's look at the back EMF. Let's just look at one of the phases. Okay. Okay. Actually, yeah, the blue one is a combined, right? Okay. So this phase, actually, probably take to see something similar to the PowerPoint. I think I'll take the first phase instead. Okay. Here we go. All right. So what do I have here? My back EMF, as we said during the PowerPoint presentation. Back EMF is really impressive for this new machine. Okay, compared to axial only or radial only. So it's almost the sum of radial and axial, less than the sum, but it's really impressive back EMF we can obtain. Okay, so it's really high power. Okay, I can plot also the torque. Okay, and that's going to be the cogging torque. Okay, for the three configuration. I think it's the cogging torque is TZ. Okay, and yeah, and as you can see, I have a higher torque. Okay, when it comes to the combined radial axial machine. Okay, so that's one set of results comparing the three machines when it comes to and this one is of course a no load analysis. I can also show you the comparison of the RADAX or the radial-axial machine for different RPM. Okay, and again I can compare results, magnetostatic results, and I can show you the torque. Okay. No, actually, I'm going to show you the back EMF. Okay, and I'm just going to choose one point. I'm going to add this at that point only. Okay, showing you that the back EMF, okay, as a function of RPM or speed of the rotor is inversely it's as we go up in speed, we have a higher back EMF. That's the takeaway from this plot. I can also compare the torque at this point, okay, and also showing you the torque, okay, of the same RADAX machine at different speed. Okay, so this one is the what we call the no load analysis. Let's look at some load results. Some load results, and because this one I wanted to do thermal, so we do coupling. We have thermal coupling and motion coupling. Okay, and then the next study is same thing, but this one is transient. That's what we want to show you. So, so the first set of results, okay. Again, this one is of course it's a dynamic analysis. So we have more actually results, and the results stable. So you have the force, torque, current, inductance, flux linkage, induced voltage or back EMF, okay, solid loss, winding loss, core loss, energy, so on and so forth. All of them are at your fingertip, okay. And again, the plots are the plots. You know, you can do the same thing. You know, can animate and so on and so forth. You can look at the results stable now. You can look at the induced voltage in the three. Okay, this is the induced voltage. Okay, this is using loaded analysis with load analysis. Okay. Any of other plots, again, as I said earlier, are available. Okay. This one is I can of course do the torque results, torque TZ, okay, and there you go. This is my torque, okay, as a function of time, okay. This is a load torque, okay. So in addition to the electromagnetic results, okay, we have thermal results right in the same interface. That's what we call it, integrated thermal solver. That's what it means, because you don't need to export the electromagnetic loads and the dissipation and blah blah blah, and go to another software, another window, and export and import. None of that is needed, because you are an EMS. An EMS allows you to actually, right in the same interface, same window, you have the electromagnetic input, thermal input, and you can specify any of this thermal constraint. In this case, just convection, okay, natural convection. Okay. Similarly, the results are also in the same interface. No need to export to another window. So show you the temperature distribution, okay, and this is what I showed you in the PowerPoint, okay, is the heat, the temperature distribution in the stator core, okay. So both the load analysis, I can do steady state thermal or transient thermal, okay, and this one is of course using transient magnetic, okay. So to conclude, the RADAX or radial-axial flux machine is a promising new machine that started surfacing in the literature. That's why we wanted to bring your attention to this new machine that people start. It's just still in research phase, but it's very promising because it gives very high torque and a very high back EMF compared to either radial only or axial only. Okay, so these are very important two features. Okay, yet there is a drawback that must be overcome before making it a viable design, viable machine, is the axial force acting on the rotors, the axial rotors, because we know that a large force can actually deform or even break the rotors altogether. So, and another drawback is the cogging torque. The initial cogging torque for this type of machine also is higher. Okay, EMS allows you, right inside SolidWorks, it allows you to study, design your simulation, all what-if scenarios for, and coupled to SolidWorks motion, coupled to thermal, and we also have coupling to structural. It just been showed in this particular case. You can do all kind of what-if scenario. You can optimize, do a parametric study, and that allows you to really fully study, to virtually prototype your machine before getting before any prototyping attempts. With that, I would like to thank you for your time, and now we open the floor for questions. If you have a question, please type it on the right hand side of the chat, and we will be glad to answer all of your questions. And thank you again.